sure that you're all very tired by now. We will try to be as fast as we can and wrap up, because then we can look at the mind and the Texas mind that Martin and Fabio Vitello are going to show us and will explain to us, so we can see how the tools in 3DTeLC work. So we're here, Hugo Becciani from INAF, and I'm Mel Krokos from the School of Creative Technologies in Portsmouth, and we represent the technical people in the consortium in 3DTeLC. Actually, we have one more partner, who is in Hungary, right? And they're working with high performance and grid computing and so on. Unfortunately, they're not able to be here today. So basically, these are the technical people working in this project, developing the tools. So we'll give you a quick idea about ourselves, where we come from, for you to really see that we come from a totally different area. We're not scientists, we're not geologists, we're not, so we try to understand.
This means that sometimes we speak different language.
Yeah. In fact, quite a lot of times, right? Yeah. So then the idea is for us, we try to understand what you want, what are your aspirations, what you really want to do, and I think also many times you also try to understand what does it mean to develop software and develop tools and things and so on. So just to give you a very quick idea about myself, I come from the Creative Technology School in Portsmouth, and I'm involved there in work both in teaching but also research in terms of graphics and visualization. I'm interested a lot in emerging technological solutions, and especially in bridging the gap between computing, arts, and sciences. And of course, I'm working also with in areas of virtual reality, and that is part of what we're doing in this project. So our school is a school that is a mixed school that has got both artistic people but also technical people, and we belong in the faculty called the Faculty of Creative and Cultural Industries. And basically what we do is that we develop the highly skilled and expert arts and science graduates for creative and cultural industries of tomorrow. So we have degrees, for example, that have both paths, like a computer games technology degree, but also a computer games arts degree. We have a Bachelor of Arts in Animation, but also a Bachelor of Science in Animation and Visual Effects. So we work in areas like animation and visual effects, computer games, digital media, but also film, music, and sound technologies, virtual reality, but also things like motion capture, and so on. So I will give you a couple of ideas just to really see where we actually come from when we try to approach you within a project such as that has actually won a prize for the school in the National Festival for Computer Animation in the UK. And there's a sound here. It's a 2D animation. Movies, right? 2D. So you have to do the storyboarding, the design, then you have to do the painting, you have to create the animation, put everything together, do the direction, so do the complete thing. There is also work from our students that has been submitted to the national competition for animation and won the award. Right. Another one I can show you is this one. This is quite interesting. This has been running now for a number of years. Basically, what we said about 5 years ago is that it is possible to create a full Hollywood movie, just like Hollywood does, but only with students and only with us directing the movie. And doing everything, like the compositing, the painting, the animation, the modeling, the texturing, everything. And this movie is called Stina and the Wolf. It has become quite a great project by now. And you can see here a trailer. So you have all the special effects. Everything is done within the school.
It's nice to find somewhere peaceful.
The animation there, the grass. Here, special effects. The clouds up there as they appear. The model. The teeth, the hair, the snow falling. The characters. Look at the blood there. Yeah. The horse, the kinematics of the horse, the physics. I can imagine so the humans as they are animated. So it's a lot of skills as you can imagine, including also coding and how programming stuff and so on. As we don't have that much time, then we do one of the largest game jams in the UK. So every year we have students coming from all over the UK organizing a game jam, which they spend about 1 week, and then they have to create a game out of nothing. So they can use any game engine, like for example Unreal or Unity or other engines. We give them a competition, and they have to create a game, and then we give them awards. And this has been one of the most successful in the UK. It has been running now for about 7 years or so, I believe. Then we're doing things like this. So if I go here to that, so this is some work that the school has done some time ago for the London Symphony Orchestra. So their director came to us, and what he said that they look for a new visual identity. They're looking for branding. So the idea there was to use music and sound, compose, try to put it together with animation, animate, and create an animated feature film for them to show their new visual identity. And we came up with this, which actually are using. I'm sorry about the sounds, but I hope you can still hear it. So there's some special effects there. Done specialized software packages such as Houdini and so on. But the idea here is to synchronize with the sound, but in such a way so that you see at the end the LSO comes up, the London Symphony Orchestra sound. Okay. But then we also do other things, like, the people we have are both artistic and technical. So we're doing things, for example, like, let me just stop that. Like, for example, facial recognition. Like, for example, deep learning, like, for example, high-level hardcore coding. So let me give you an example here from a simulation. So this is a simulation that was performed, it's a cosmological simulation in Switzerland last year. It is one of the largest in the world, and normally what they do is that they run the simulation for a long period of time, and they create snapshots. Now, it's a time evolution. So the snapshots here are 2.5 terabytes each. And here we have visualized 260 stars. So together. So you can imagine it's a quite large data set. So there's over 1 billion years of evolution presented. And you can see here how beautifully, as the simulation progresses, the various tracks there are formed slowly. So then we move towards them and try to, walk around and look how these things are happening. You see some very beautiful animations coming up now as we get closer and closer. So it is quite demanding data set this. And the idea is that if you have a supercomputer, you can produce the data, and you want to be able to visualize, you need very high performance rendering, for example, and algorithms to be able to do this.
Do you know what is this?
Yes. This? Yes. Right. Shall I say? Okay.
Galaxy
So
formation. This is
yes.
galaxy.
So it is done at the University of Zurich by Lucio, actually. Lucio, you know Lucio? Yeah. So, yeah. Okay. Right. And then we also do stuff like virtual reality, but also other things like, for example, cultural artifacts, like reconstruction, for example, of old sites. We work a lot, for example, with architectural boards, but also with English heritage. So we constructed stuff like, let me see if I have it here. Oops. There, for example. So this is a place called, okay. If I go to the beginning. Okay. So it's called Bishop Waltham Palace, not very far from Portsmouth. So there was a bishop there visiting every now and then. It's a very nice palace, but part of it is remaining now. They were producing beer, they were making bread, right? So what we did here was we went and did some photogrammetry. Then we have collected other data and images. We have collected historical data out of records that we have, and we try to fuse all together to reconstruct the life as it was then. And then that way to try to understand the cultural value of how these people lived, what actually they produced, what was of value, and so we try to see the way the world was at the time from today's point of view, and try to understand it better. So it's a cultural heritage reconstruction of this. So I can stop this now. Right. So if we move now into the virtual reality, if I go and continue there. Oops. Right. Okay. So the first question is that what is virtual reality, right? I know some of you have been in the previous school in Portsmouth, but others are new, right? New faces, right? So do you all know what virtual reality is? Yeah? Can someone tell us? Can you tell us what virtual reality is? Yeah.
I'm not sure what.
Oh, you should have said I don't know that. Right. So what is virtual reality? Okay? How can you define it, please?
Could be the reconstruction of reality virtually.
Yes. So you could say, if you could go there, you could say basically reality, real reality, right? This is the world in which we actually live, right? And then virtual reality is basically a simulated part of our world, or you can call it imaginary world, right? Using high performance computing and sensory equipment. So there are three things there, right? One thing is the computer in the middle, and then we have sensors on one side, and on the other side we have some way to be able to immerse into that reality, right? So you have like headsets like the Oculus or Vive or whatever, so on. And then you can have like gloves or other kinds of sensors. And you need a computer, the high performance computer there, because this guy has to be able to track what you're doing there in real time, right? So you cannot have something that is of low quality and so on. So the main ways that you can put down, the main keywords you can put down for virtual reality are there. So basically you can define this as a believable, interactive, 3D computer generated world that you can explore so that you feel you really are there, right? And this is both mentally and physically. So basically it's an illusion, right? It's an illusion, right? And then you get immersed in there, and suddenly it's another world, right? And let's look at all those words one by one, the keywords, what do they mean? So the first one is believable, right? So you really have to feel that you are in that virtual world, right? You know, or whatever, or the moon, or whatever, and so on, somewhere, wherever. But whatever is there, you really have to believe that you are in there. So you have to leave the illusion. The other thing is that it has to be interactive. So as you move around in the world, in that virtual world, then the world also needs to move with you. So you're part of the world, and the world, you talk to the world, and the world talks to you. Right? So you can watch, for example, a 3D movie, and be transported up to somewhere, like the moon or something like that. But this is not interactive in any sense, right? You just watch it, you feel you have gone there, but you don't really interact with it, right? So interaction is very important. Then it has to be computer generated. This is very important, of course, because you really need powerful computing to be able to do that. That's why the computer is there. And then it has to be explorable, right? And immersive. Explorable means that sufficient size and details to allow exploration of the world around you, right? So you can have, for example, a painting. You can look at the painting, it will be extremely realistic, right? But that's not virtual reality, right? So the world has to be in this way to be able to qualify as a virtual reality world. And finally, it has to be immersive. So it has to be both believable and interactive. So effectively, it has to engage both body and mind. So these are the main categories that we normally put down to classify something as a virtual reality. Please go ahead.
I have a question. This might be semantics, but you don't highlight 3D. So does virtual reality not have to be 3D?
Well, normally
or
it
is
is
that obvious?
yeah, normally
Okay.
it is
I didn't
in
know if
yeah,
it was
yeah,
2D.
yeah.
Okay.
Okay, so then if we move further down, what virtual reality is not, right? So it is not something like a partial glimpse, let's say, to another reality, right? Like those you get, for example, if you sit in a cinema and you look at a movie with a lot of drama, and maybe you can see somebody jumping out of a plane, and you know they're going to be killed or something like that, and you see the director directing like the way they see the movie, and you feel it, and you feel very immersed into this, but this is still not virtual reality, right? So in virtual reality, the illusion should not be broken by turning your head, right? Like you're going to start where I'm getting at, because effectively we have an illusion, and we have to live this illusion continuously in a seamless way, in a way that is smooth, in a way that it makes you living it all the time continuously without being broken at any time. So it makes you think that you're actually living inside the virtual world, you're immersed. That's where immersion comes in. And this immersion can be either partial immersion or a full immersion. And of course it is not passive, so it is a two-way interactive. So you respond to what you see, and what you see responds to you. So there's a kind of dynamics in there. So, if we move further down, so there's various types of virtual reality. So one is fully immersive. So normally you have a rich virtual world here, you're fully immersed into the world. So I would imagine you have a very powerful computer to be able to track users and adjust the experience of the users accordingly in real time. And effectively, what you have there is that you normally have like a head-mount display, or you might be in a very large room like the virtual reality room we have in Portugal, for example, where you might have like speakers and displays, large displays, showing images that are projected from outside this world, and you're immersed in this world, and you live the dream, right? Okay, another one is non-immersive. Oops. Right. Okay, so here, for example, if you look at the picture there, try to find the picture that relates to each one of those concepts. There, they have a flat simulator, right, on a home PC, but this actually might qualify as a non-immersive virtual reality. They don't have glasses on, right? But what happens is that they have a wide screen or multiple screens put around them, so they're immersed in some way, right? So they have headphones, and surround sound, a joystick, and other controls. So, and effectively they create this kind of illusion again, that you can be immersed into that world that is presented there. Okay. And finally, we have the collaborative activity. So here, for example, like virtual world games, for example. So these meet criteria that are believable, they're interactive, they're computer created and explorable, but not immersion criteria. So they offer the idea of sharing experiences, and that is a very important thing in the way virtual reality is moving on, as to sharing and collaborating and being able to do things from separate. In fact, this was also a little part might be written somewhere in 3DTeLC, right, about sharing experiences, right? I believe, yes, somewhere with just a couple of sentences, I believe in some deliverable, yeah. So the idea will be, for example, if you had like the tools we have now, you could share them remotely, and then work and collaborate together and come out with results that you have discovered together as a team, but from different locations. Okay, a close relation to VR is what they call augmented reality. I guess you probably all know this, right? No? Because this is mainly because, you know, these phones, and I mean, most phones now, they have this kind of stuff, right? So basically here, it's an enhanced experience of the exact reality we see in front of us. For example, there, look, you have data that you can display in front of other data that you see in the real world. So you put your phone there, and you can superimpose the data, right? So neither of these worlds is virtual, but the idea of exploring and navigating the two simultaneously has a lot of common things with virtual reality. So a lot of the techniques are similar, the problems that you require, for example, synchronization, for example, in a way that is seamless, and so on. So, lots of equipment that are out there to be used for virtual reality, like handheld controllers and these treadmills. In fact, Charlotte, we have this in Portugal, right? Yeah. So, which one? I think we have the camera, right? Also have the treadmill? We don't have a camera. Okay. How about the wheel dish? Right, yeah. So lots of equipment out there that you need to do that. Okay. And of course, there are various types and applications, like in healthcare. This we talked, if you recall quickly, also in the Portsmouth school. So I'll just go through quickly, or to visualize the scientific data, for example, like the data I showed you before from the simulation. So you can embed them into a virtual reality system and visualize them. Or like in entertainment, for example, or in education. And now it brings us now to 3DTeLC, yeah? And the tools that we want to create here to be able to educate people. So, in this time, relating to geosciences. So when we move geosciences, the problem we have here is these geological scales, right? I hope you understand now better, maybe, right? I start moving this here, right? They're not match very well with human scales, right? So you might, you want to be able to dig and see somewhere deep into the ground, right? Or you might want to see something that's an evolution of very, very many years, but it doesn't happen that you can see it in front of your eyes. So basically, there is a mechanism of being able to control both the spatial and the temporal scales that are involved in disciplines like yours, like geology, right? And basically, what we're looking here is to put everything in your hand there, right? So to evolve the way you work by making immersive visualization using virtual reality accessible and collaborative tool. And effectively, what we want to do that is that why we want to do that is to help you to be able to assess geohazards. So that's why virtual reality is a prime target to be able to do that. So computer games engines, this have evolved a lot over the last several years. So two of the most important and also the most widespread are Unity and Unreal. In 3DTeLC we're using Unity. Why are we using Unity? There's a reason for that, right? There's a big discussion about that. So finally we
tomorrow in the next presentation we'll say.
Yeah. And normally you need like programming skills, so it's easy to transfer results across different communities. But you need to take care of other things like smooth movement to ensure this mind map consistency and thus avoid motion sickness, which is a very big thing you probably have heard about a virtual reality environment. Because basically you create a mental map. This map is mapped to the system that you are immersed in, and you have to keep the consistency as you move around and as you interact. So you also have to be conscious of how different scales of subjects affect movement in virtual reality. So you move, you interact, but then you have subjects there that can be at very different scales. In fact, in 3D we have that, right? We have like very small features or very, very big features, right? So you have to be conscious on how these different scales affect the system. And in fact, until now, we have worked actually quite a lot in calibrating and trying to ensure that the movement and the way that we interact with things in the interaction mechanism is appropriate and suitable and smooth and continuous. It's not easy to do that. Okay, so now we'll talk about projects that are existing out there. So Hugo will take over to talk to us just quickly about the projects. And then I will continue with 3DTeLC and come to the point where the tools are at the moment, give you a very quick overview of the tools. And tomorrow, we will see the tools in more detail. Also, there will be a presentation from Fabio Bonali to give more hands-on experience of the tools. And after this talk today, we will show a very special area in Santorini here, which is the mine, in terms of virtual reality. Okay, good.
Okay, we speak about the Argo 3D project, but this is also an opportunity to present my job. That is very different from your job, as I said at the beginning. The story and the Geohazards have nothing in a common area at the moment, but there was the common way that we decided to join with this community because we used the three-dimensional visualization of data. You remember the galaxy formation, this galaxy formation we started from this. So we started the collaboration with this community based on our experience on 3D visualizations. Okay. Okay. The Argo 3D project is an Italian project. Have some aspects that are very different from this project, 3DTeLC, but other aspects that are common. The project was an answer to a call that was from the Italian Ministry of Research for Scientific Dissemination in 2015. And the fund scheme for answer the call was a consortium between Italian university research centers. Together with Milano Bicocca and the Cometa Consortium, the leader is Milano Bicocca, Professor Tibaldi, we submitted a proposal that was submitted in August 2015 but the answer approval was on January 2017, and the first funds we received at September 2017. So we will last the project up to September 2019. The goal of the Italian Ministry was to development of research and experimentation of methodology for effective teaching of science. So this was made to promote dissemination both at national and international levels with exhibition initiative, conference, and so on. Our proposal had the following two main objectives. It was to promote scientific dissemination, so it's different, very different from the purpose of this project, that is for university, for Erasmus students, and so on. And to develop also innovative methodology and technologies for to improve the teaching of the geohazard science. In this sense, maybe that some useful contribution can be given by the two projects with the 3DTeLC and Argo 3D. The idea of Argo 3D is to create a public information platform that will allow to present the different models in 3D, like 3DTeLC, allowing them to interact with this model, like 3DTeLC. But the problem is that the approach is for the dissemination, not for students or lessons with students, like this. The technical partners is represented by Consortium Cometa, that is for creating a three-dimensional and virtual reality platform using the Oculus Rift and also 3D projector that can be used by special glasses to look in 3D dimension. And the partner is UNIB, as you said, that they have competence related to geological mapping and structural mapping. The group carry out field trip to the drone survey, is expert in data visualization, but Alessandro Tibaldi and Fabio will tell more than these few words about the expertise of the group. And the other partners, as I said, was the Consortium Cometa, that was an agency that we found together with the National Geophysical Volcanology Institute in Italy, with INAF and the Free University in Sicily. This was made at the beginning to create an high performance computing network in the Sicily. So it was located mainly for our land. Now the objectives, the view is enlarged, and we collaborate with many institutions in many sectors to provide the services for ICT in general. INAF is a partner of Cometa Consortium, like INGV, Danilo is here, and Susanna. But I want to spend just a few words about me and my groups, because Fabio Vitello, that is here, that will work with you, came from this group, and so it's better that you know the real our competence in the ICT and in astronomy. We were involved in many projects. We are few people, so we are at the moment 6 persons, 7 persons in some periods. But we were involved in many important projects, starting from grid computing and visualization in EG Spire and the SciBus, that was to create the science gateway for visualization, for three-dimensional visualization. The product that we call it Visivo, that was to use the visualization in 3D in the environment of cosmological simulations. And then there were the new important project. It was another important project that was found by the Italian Ministry for inspecting containers for nuclear contraband materials, using, and this was the question that I don't put this morning for you, Alessandro, the cosmic muon tomography technique. Now this technique is also used, start to be used also to inspect the caldera, the magma camera, sorry, the magma camera. And maybe that NGV have already started some project together with the Department of Physics or the engineer. I don't know what you are involved in, but we worked for the tomography inspection in the visualization in 3D of the elements inside a black box that was a container, in our case, looking for urine and for suspected materials inside the containers, for safety reasons. Then there was also Via Lattea, that it was an important project that we created special clients of Visivo for the visualizations of visual analytics systems to inspect the star formations inside the Milky Way, our galaxy. And now we are involved also in other projects like Pilot, where we are continuing the visualization with the Visivo Science Demonstrator, that is the product that we developed for Via Lattea, but using in EOSC. EOSC is the European Open Science Cloud that will be found with a lot of money, bought money from the European Union. Myself, personally, I am involved in the EuroExa. That is an exascale project to create the HPC of the future that will use the roadmap of the exascale that will be found by European Union, and I am porting the HPC codes that we use for the Gaia projects. It's another important project in OPS and FPGA, means the new frontiers of the HPC in the next few years. The future start now, in this sense. We are also involved in 3DTeLC, and in other projects that is important about CHIP project is just to provide a computing facility to enough institution. But another important project where we are involved, mainly for HPC, is the Gaia mission, where we created an HC software that will be used to map 1 billion of stars of our galaxy in order to understand the formation of the galaxy, and in order to understand if which stars forms planets and which planets can host the life. Okay, so you can study in the future the landslide and the eruption volcanic in extrasolar planets, for example. I think 300 or 400 years, maybe. Okay, maybe in any case, the bigger project where we are involved is SKA. I don't know if some of you know this project. Is the so-called the Square Kilometers Array. That is a unique telescope. You have to imagine a unique telescope that starts from South Africa and finish in Australia. That will have about 1,000 of dishes, like on the right picture, and million of low frequency antenna to study the universe and to understand many things about the dark matter, the dark energy, and you can imagine which effort we have in terms of visualization so big of data that we need. And in order to understand how much is big, if you compare this number, SKA will produce about 300 of petabytes per year. All Facebooks produce now 180 petabytes per year, and Google 98 petabytes per year. So there is an order of magnitude, more or less, about some kind of social networks that we use with the data that we will use for SKA. So this is a big challenge for us to manage the data that will come from the SKA survey in terms of visualization. We are involved, mainly my group is involved in the local monitor and control of the dish of the SKA, and in NES, that is the project that will establish the rules and the main roadmap of the computing centers that will manage the data from SKA, and together with the South Africa and the other country, we are considering to deploy unique systems of managing the data in SKA. It's a very big experiment, a very attractive experiment. Another experiment is very big experiment too, is the Sharing Computer Telescope Array, CDA. That will have 100 of telescope located on north and southern hemisphere to study the gamma ray astronomy at a very high energy. In Catania, we host the ASTRI telescope, that is one of the, like we can say, the precursor of the telescope for CDA. And my group is also involved mainly with Alessandro Costa in this kind of projects. Okay, I go right at the hand. So, coming back to Argo. Argo will develop software for navigation real-time in 3D reality. We have continuous feedback between programmers that comes from Cometa and users, and that comes mainly from the universities, mainly from mine and Bicocca. And we also have some dedicated computing server to manage big data in Catania, using also system equipped with NVIDIA GPUs. And what we can say about the difference and the point of contact between the two projects. Partners are different, okay. Even if INAF, that is part of the consortium, is part also from Cometa and from 3DTeLC, and Unimib is bought from Cometa and 3DTeLC. The final mission of the two projects is different, the final target audience is different, as I said. There are some similar aspects in terms of developing of features, and the features that we develop for Argo 3D can be also, in part, used also for the purpose of these projects. And this is not a problem, but it's a gain of the projects. Okay, to conclude, I want also to mention this activity that was a project that was approved also using the Argo 3D possibility, founded by the European Geoscience Union and led by Fabio Bonali, that is shaping geological 3D virtual field survey for overcoming motor disability. In particular, the event is scheduled on December is to allow the students that have reduced the mobility to go inside systems using the virtual reality and to inspect things that they otherwise cannot inspect. But more details can be asked directly to Fabio. Okay.
Where we left it off before. So just to connect with what Krokos was saying before, with a project like the SKA, for example, it is very important to be able to today understand techniques that we can visualize big data. What I showed you before, that simulation that was made in Switzerland, which we have visualized in Cosmos, is at the very limits to be able to visualize this interactively. So this actually was produced in a supercomputer in Switzerland and was visualized in a Cray cluster that is in the United States. And the idea there is that for SKA, they run, for example, on the Pathfinder missions, right? And in those missions, they collect data to try to calibrate, to be ready for the actual data stream start coming in. And what happens is there's not enough space. So you do get data, right? But you cannot store the data for a long period of time. So every now and then, they just have to delete the data to store the new data, right?
No, you have to consider, for example, just to comment your suggestions, that 90% of data that we collect at the antennas will be immediately deleted after the separation. So otherwise, this number of 300 petabytes becomes 3,000.
So imagine there's something really important there that can give us a really important clue about understanding the structure, right? But we don't have time to actually discover that. It's a very limited amount of time. So we have to prepare from now for the techniques when the data comes in to be ready to apply them. Yeah? And there's a very long curve there to work and improve things like rendering. And of course, what we're talking about here is that we want to do that and fit into virtual reality, right? And then for you to be able to interact with the result and so on. So the pipeline is very long, very complex, and it is not easy to think how to scale it up easily at this stage. So let's go back to the present now. We're still in 3DTeLC, right? And we're doing what we're doing. So what we're doing here is that we're using Unity, as we said. So the idea is to have an integrated suite of seamless navigation VR tools. And we're looking to be able to do mapping, to do measurements, also to support field activity and so on. And the key ingredient of 3DTeLC is this combination of onshore and offshore, right? Putting them together and being able to experience and visualize them and interact with them. Oops. Right. Okay. In a seamless way, right? So what we're looking here is to tackle the skill shortage in geosciences, like Malcolm mentioned to us in the morning in his introduction, and of course use this as a basis to try to support the pan-European postgraduate curriculum. So effectively the idea is to train the geologists of the 21st century, right, that are competent in using emerging technologies such as VR, and that they will be able to tackle big data, for example, as this comes along. But you see in other areas, for example, astronomy, it's coming along already now, right? And it will come also in your area too very, very quickly. So if I move further now, so the guiding principles here are to simulate the field mapping experience and the observational behavioral scientists. So that is also why we want to be able to observe what you do, how you do it, understand, break it down algorithmically into constituent parts, and then to be able to validate this from the VR point of view, from the computing point of view, rather than from your scientific point of view. So the data are from UAVs and ROVs, and results should be some demonstrators to show onshore and offshore. And that's also a question that, Malcolm, this has to be answered very quickly, right? So what models and what demonstrators, because they will come into the middle of the project, right? So the middle
further the way through.
Yes, yes. So it has to be decided very soon what are the demonstrators, what is going to come out of all that, so that we can start working to produce them. And another nice thing about all this is that all these tools are open source. This means that people can look at them, they can build upon these tools. Then we can start having a community to start building upon this and creating. And you know, software is something that is live, right? If people don't use it, if they don't develop, if they don't contribute, it dies, right? And we definitely don't want this to happen. And of course, we want to have advanced navigation controls, like to be able to on-the-fly visualization and adjustments, and have this, what we call rich interactions. That is really, really important in order for tools like that to be successfully used. So there are 3 types of navigation modes. So on the navigation we have the walk mode, the flight or boat mode, and the UAV or ROV mode. So the walk mode is just when you walk in a scene at various speeds. Actually, the idea there was also to calibrate that, like what is the correct speed and slow and fast and how fast, and maybe different people go different ways and so on. The height that you start from after the look and so on. The flight or boat mode, so flight for the onshore and boat mode for the offshore. So they use it to be able to fly, navigate, and look at the terrain, orthogonally from above, like a projection, right? So I will tell you more details about this, and you will see hands-on experiences tomorrow, right? It's a session, we have a technical session in the afternoon, in which there will be lots of presentations, so you'll be able to experience all these tools. And then finally, we have the UAV and ROV mode, where the user is free of moving interaction, just like a drone or like an ROV device. It is a simulation of this. A number of tools that are there are tools like for setting place mark, marking lines, creating polygons, measuring areas of polygons, surface areas.
Tomorrow we will present in detail the different tools Also with the practical use of the tools.
Counter experience, yeah.
Like
So this has
Fabio, Bob Fabio. Fabulous.
Then measurement tools, like looking at topographic profiles, for example, those two rulers there, actually I have measured them, but okay, this probably will be measured because the functionality is the same, it's just the ruler that measures. It doesn't matter if it's horizontal or vertical. But at this stage, the idea was to have them separate, to tackle the problem so we know that it works and works well and test it before actually they're merged. And then stuff like compass, like being able to write field notes. I remember, Derek, in your questionnaire, you wrote that. The questionnaire that we released originally,
Yes.
you are among the only ones that wrote down field notes. Yeah.
No, it was very usable.
Yeah, very useful, yes, yes. So then a camera to make pictures at different parts of the flow as you look into the VR environment and explore, but also GPS tools like getting information, like setting waypoints and having an overview of the whole scene, or tracking, and be able to export these things but also save them so that you can afterwards process them. And then the idea in that way is that to be able to follow the whole workflow and how the user experiences the virtual reality environment will have reconstructed. So, if we go to one of the last slides here. So basically we have a couple of models that we can experience. So two models come from Krokos. There was one model that comes from Athens. So this is the mine, the Metaxas mine. So these models you can experience. You can also experience in VR, also with the Oculus, but also with tools. So you can make measurements like I showed you before and so on. So the machine we're planning to have it, everyone can have it in the hotel, right?
Yes.
So, yes, yeah. And then together with that, we have started looking at ways to validate how the actual VR tools work from the VR point of view. So there is a questionnaire. You're going to receive an email with a link to that. At this moment, it is anonymous. You can just fill it in with the data after you have played with the VR. And then we want to collect this data and start making a very first map of the potential users, which is you, right? Both professors and students. And start building up a profile to see how these tools in terms of VR, like for example of navigation, in terms of experiencing of different objects into the environment and so on, work. And the plan is to use this as a basis to start planning individual studies for individual tasks. For example, the task we're going to do on Monday, this is a very specific task. There's like a starting point, there's a number of different features that has to be recognized. There's a couple of measurements that have been taken. All these things have to come together. And then there has to be an assessment of geohazard. And this can be replicated in the VR environment, but also we can collect real data by watching you guys doing it in the field. And then we can actually try to compare and contrast the real and the virtual. And in that way, maybe we can see things there that can help you doing things better in reality, out of the virtual reality. Maybe we can see things that are deficient in VR, and we can see how you do it, and we improve the virtual reality. So it is two ways communication. Anyway, so that is the plan. So you receive an email. I think Evie, you will email all with the link.
Already, I was driving.
No, not already. I mean later tonight. Yeah.
Yes,
So that we can start the questionnaire, and then we'll start building all these studies. Great.
Okay, but I think that tomorrow we can show the data questionnaire.
The last slide actually had it there, which was for Ugo to take over, was the slide with the log of Back to the Future. Because we moved back to 3DTeLC now, which is now. But Back to the Future means that now we have to think, okay, so we have this big data, the rendering, the new visualization techniques we develop, the scalability to be able to move up. We see this happening in other areas like astronomy and so on. It will be happening very soon in geosciences. So what do we do about this? How do we think about tackling this and moving into the future? So this is a brief overview of the possibility of this proposal we have been looking at some time ago. And the idea was to resubmit now under a new call that is coming up.
What happened in your futures? The problem is that probably the future is not more given just by only a research field to stay alone, okay? But now, consider the big quantity of data that we have to manage, the big data problem. And ever and ever you will need different competences companies to work together for extract the most deeper information that you can imagine to now from your data. And this is the challenge for today, the challenge for tomorrow. So we have to consider that there is a big effort of the community in building, as I said before, the European Open Science Cloud named EOSC. It's a big quantity of money. Why this? Because the European community believe that now is the time that the computing infrastructure will be the fundamental part of many science to manage big data. So for this reason, the European community created a project called the EOSCAB, that is a sort of common platform with some point of access, like an hub that you know, with different kind of science. But all the science have in any case an important point that is the data life cycle. Data must be created, ingested, calibrated, elaborated, stored, extract the science, and then the cycle will start, because there are new other information that enrich the older data, but together forms the knowledge in the project, in a science. So this is the context where we will work in the future, not only in astronomy, but also in geophysics. Okay, and the particular cause that we will try to apply in the next features in the next month is the InfraEOSC H2020 project call, that is to develop an agile and fit for purpose and sustainable services that pay attention to the underlying part that satisfy the evolving needs of the scientific community. So we are starting now to think in the future. Okay. The scope of this course is to create services. Put attention. We have to create services for data that address some aspects of some specific science, like the geophysics. Really speaking, this call will open the possibility to think in different way the same computer science in order to create services for the community. Because up to now, we have another proposal that we call it Day One, okay, that was an older consortium made by 12 partners that create a proposal to have a specific data, and they want to be helped by the computer science. No, this is not the right way to think again. But we have a base that is formed by the cloud, in terms of generic cloud, commercial cloud, of HPC cloud, and services that must be created for analysis of big data, and like the case that we have in Geohazards. The previous proposal was accepted for funding, but no money was put by the Commission for budget restructuring. And unfortunately, we cannot more present this kind of proposal, because now the target of the European choice is changing. We have to create services for the data. And for this reason, I go directly to the last slide. We have to think at different kind of levels. There is the Geohazards community on the top levels that have to create some knowledge for him, but also the data are not restricted for him, but must be open. Open means, for example, to protection civil agencies or other agencies like insurance. Because imagine that you want to build a house in the landslide movement zone. I don't know, Malcolm will say, oh my God. But also the insurance is saying, oh my God. Okay. And in any case, open be shared with also other communities, like archaeology, because archaeology and geophysical have some very similar aspects. And this is the top of the level of the structure that we have in mind. Probably you belong to the top level of this part. But then what is under this level? There is the infrastructure. That means the different levels too. One of the levels is the access to the real computing systems. So we have to create a science gateway, scientific gateway, because I cannot ask you to manage the HPC infrastructure or the cloud because you don't know nothing about this. So I have to create a level called the scientific gateway that is in your language, speech your language, to create workflows that can run inside a complex infrastructures. Okay. And this infrastructure has different services on top.
That is the reason why we insist very much in workflows, to try to define the workflows, and try to understand how the things work in the context of those workflows. Because here the trick is how to actually decouple the layers one from the other and make them as independent as possible.
Yes, exactly.
Yet seamlessly integrated so that it's possible to work at one level without having to know the details of the level below. And that is the whole trick here. So that you can work at the top level as a community, use some tools, employ, I believe, there's 4 different services there. There's deep learning, there's creative visualization, and there's another 2, right? I cannot read from here. Right. Yes, the immersive. Yes, so what we have here is immersive VR experiences. We have deep learning, we have visual computing, and then we have data products, life cycles. And all these 4 things are very closely integrated into the middle level, the middleware, feeding the level above where you see your portals and where you run your services and so on as communities, and talking seamlessly to the infrastructure underneath, which is the actual grid, or a supercomputer, or a cluster, or some form of distributed computing.
So, what is your responsibility? Your responsibility to do science, but also to create a way to imagine to do science in terms of workflows, because the workflows is in the line of the border of the upper level and the second level. What is the responsibility of a computer science, like me? I am not an astronomer, I am an engineer in computer science. Is to create the system to mask this. And there are 3 levels of the infrastructure. The level of the gateway, because to do the gateway we need a knowledge of how it means to create a science gateway. Then there is the level of the services that are scientific computing services that involve all the fields that Mel said a few years ago. And at the end, there is the real hardware. The real hardware. I cannot ask you to imagine how to store, how to preserve, or how to make the data preservation. Because if I speak to you of data preservation, you say, oh my God, what have you to do? Just a copy. No, it's not just a copy. It's a more complex story. And imagine what means this, now link my works with you, this for SKA, 300 petabytes, and data preservation, data curation, and data life cycle, bring together with your work and my work. Okay? So for this reason I am here. So I don't want you to annoy more, we'll last 1 hour. So, but this is the reason why we are looking for the future in this direction, with this consortium.
And that's exactly why in those workflows, you have to look at the different stages, and we have to understand from the very early, from the very beginning of everything, how these things are broken down into their constituent parts, computing speaking, let's say, to be able to encode them as workflows and to be able to insert them into a system like that in the future.